Hi students, in this first video for online lecture 6, we're now going to go into chapter 4 and start talking about electron configurations, periodic trends, but today we're going to start with a little bit of a review. So as we go back to our quantum numbers back in chapter 3, we remember that the final quantum number discusses the electron's behavior. So we can have an electron that has a m sub s value of plus 1/2 or minus 1/2. This is the only quantum number that has a fractional value. Well, this was important because this starts to discuss how the electron spins in its orbital. If it is going clockwise, we can see here that it is going to be spinning up, as we say, and that would have a positive 1/2. If we're be spinning counterclockwise, we would call that spin down, and we would end up getting negative 1/2. This was determined using a magnetic field in which we can show that even though electrons have the same electronic charge, they have different magnetic moments. So what does that mean for our atoms? Well, it's very important that we now look at two very different terms. One is what we call paramagnetic. This means that we have unpaired electrons in our atoms that are spinning the same direction. They are creating a temporary magnetic field inside of the atom. So once again, this has nothing to do with the electronics, but we are now creating a magnetic moment in our atoms. So if we look here at this 2p subshell, you will notice that I have two unpaired electrons in degenerate same energy orbitals. So this means that we are going to have a positive magnetic moment for this orbital because we have two electrons that are creating a magnetic field that cannot be canceled out. The counterpart to this is what we call diamagnetic. This is when the magnetic moment of all electrons in a subshell will cancel out. So the magnetic moment created by the left electron is being canceled out by the right electron because they are spinning oppositely of each other. This means that we must pair all electrons inside of a shell and a subshell. So as you can see here in this 2p subshell set, we have 6 electrons, 2 in each of the 3 orbitals, and they are all canceling each other out. So as we're looking at electrons, yes, we must look at the charge when we are dealing with such things as creating ionic compounds, when we are wanting to bond, but in this case, we can look at some of its magnetic field properties, especially when we are dealing with paired and unpaired electrons. So let us go ahead and look at example 4.1. In an atom of a certain element has 15 electrons. Give one set of correct quantum numbers for the 15th electron. So this means that we must go and look and see where that 15th electron should be on the periodic table. We will all agree that that is going to be in row 3, so we must get a principal quantum number of 3. Then you'll notice that it is in the p block. So this means that I must go and put in a 1. These two numbers are not negotiable. But now what can we possibly have? Well, we know that we have the possibility of -1, 0, and 1. But now let's look at our 4th quantum number. The interesting part here is that based off the location being in the front half of the p block, notice that we would have an up spin because our paramagnetic species would like to have up, up, up before we start to pair up and go down, down, down. So if it is still in one of the first 3 positions of our periodic table P block, it is going to be a positive 1/2. If it were past halfway in the block, there's a very good likelihood that it would be -1/2. So now the question for part B is the element diamagnetic or paramagnetic? Well, do we have all of our electrons paired up in that block? Seeing that we're only half filled, we know that this is going to be a paramagnetic species. So now let us go and look at our second question. An atom of a certain element has 36 electrons, but I don't want to know the quantum numbers for this 36th electron. I now have to go back and look at the 27th electron. So what does that mean? Well, we know, and we're going to see even further detail when we come to our electron configuration, that electrons like to fill in order. That means that they have the standard rules of the Pauli exclusion principle, the Aufbau principle, and Hund's rule guiding where they should be. This means that the 27th electron going into an atom, whether that atom has 2 protons, 27 protons, 36 protons, or 109 protons, the 27th electron is always going to go in the same predictable location. So this means that I can look at the periodic table and have a pretty good idea of where those electrons should be. Then I should be able to give the quantum numbers. So if I look for the 27th electron, I need to go look at element 27. If I do that, I will notice that it is in the first row of the transition metals. This means that that is going to be in our 3D orbital set. So even though it's in row 4, that is still a 3D orbital. We will talk a little bit about this shorthand notation in a further video in this lecture. But now that I have a 3, 2, I am allowed the possibilities of -2, -1, 0, 1, and 2. But finally, let's look at its location in that 3D block. Notice it is on the right side or past halfway. So we can assume based off of this that this is going to be a species that has a guaranteed last number for the 27th electron of -1/2. So now let us go and try and answer B. Is the element diamagnetic or paramagnetic? Now we have to go back and reference our 36 electrons. Do we have a full shell and a full shell? Well, if we have a full shell and a full subshell, this means that all of our orbitals have paired electrons, which is the case. So one of the things you want to look at is, does a subshell have a full set? That means that it's in the last column of a certain block. Or if by some chance it is the final atom in the entire row, typically in the noble gases, that means it has a full shell. So in this case, we do have a full shell, and this species is going to be diamagnetic. This means that all of our electrons are paired, and we would have no elemental magnetic moment. So one of the things that we discussed back in a previous video was talking about Bohr's mistakes when it comes to electrons. Reason why we come back and talk about this is that if we start to fill in our orbitals based off of our electrons, we would now see that our 2s orbital, if Bohr was correct, we would have to go and fill in the 2p next because they are of equal energy. So we know that this is not correct, because also if we were to go and fill the 2s and 2p once we get to the 3s, based off of Hund's rule as well as the Aufbau, notice that I would have to put in 1 electron in each one of these before going back. This would create highly paramagnetic elements, which are just not the case. So now what we can look at is the correct idea, and that is, if we go and look in reality, we will see that it's going to fill in a predictable Aufbau's correct position each time. So if I go and look at my 1s, I will put my 2 electrons there. If I go up to the 2s, as I see here, I would put in 1 electron and I would pair it up. So because the 2p is actually in higher of energy. So if I go to my 2, 1 quantum number 2p orbitals, now I will go 1, 2, and 3. So if I were to have 7 electrons, I would have a highly paramagnetic species. For electron number 8, I would go spin down. For number 9, I would go spin down. And notice when I get to electron number 10, I have created a diamagnetic species. If I go up to the 3s, notice that I can go 1, 2. I have also created a diamagnetic species once I have gone to the third 3, 0 s orbital. And then finally, if I go to 3p, once again, I can go 1, 2, 3, following Hund's rules, and then to go 4, 5, and 6 here at the bottom. If I go to 4s, notice I can go 1, 2, and now this is where I have to go to the 3D. So as I looked at that previous example, notice that I filled the 3D elements, even though 4p should be based off of our next quantum number. The 3Ds are actually less in energy. For our d orbitals, I have to go and fill in 1 electron into 5 different orbitals before I go in and fill those with its buddying partners. The nice part about this is that this is highly predictable and easy in understanding. The problem with it is that if we just use the quantum numbers, this can be very cumbersome of writing the same 4-digit code over and over and over and over. In the next video, we are actually going to talk about a shorthand of the quantum numbers, and that is going to be called the electron configuration. Have a great day.